or contrastive language image pre-training model. So this is a cutting edge artificial intelligence technique that aims to bridge the gap between text and images. The idea behind CLIP is to train a neural network to associate specific words or phrases with specific images, allowing the network to understand the relation between text and images. You can imagine Clip as a very intelligent image and text matching game. Now this game will involve showing the model a pair of images and text description and asking it to determine if that image and text are related. So by playing this game repeatedly, the model learns to associate specific images with specific words or phrases, eventually developing a deep understanding of connection between text and images. This clip model is pre-trained on massive amount of image text pairs which is scraped from the internet. And this pre-training process allows the model to learn general patterns between the text and images, making it proficient at tasks like image and text classification, image-based search, and even zero-shot image to text and text to image generation. So in essence, the clip model is a powerful tool for understanding and connecting text and image, which enables a wide range of applications in computer vision, natural language understanding, and multimodal AI. So how do this clip model works? Well, this contrastive language image pre-training model, it works by training a neural network to predict whether a given image and a given text description are related. And this is achieved through a process called contrastive learning, which encourages the model to learn a shared representation of images and text. It involves the following steps. First step is the data collection. Well, in this first step, it gathers a large amount of image text pairs from the internet, and these pairs can be scraped from websites, social media platforms, or other sources. This dataset serves as the foundation for pre-training the model. Second is encoding. Well, the CLIP model uses a neural network, specifically a transformer-based architecture, like the one which is used in popular language models such as the BERT and GPT, to encode both images and text into a common vector space. And this encoding allows the model to learn a shared representation of image and text. Third is the contrastive learning. This clip or the contrast limited image pre-training model, it is trained using a contrastive loss, which incentivizes the model to learn a shared representation of images and text. In simple terms, the model is trained to predict whether to randomly sample image text pairs belongs together. So if the image and text are related, the encoded representation should be close to each other in the vector space. If they are unrelated, the encoded representation should be far apart. And finally, it's fine tuning. So once the model has been pre-trained on a large data set, it can be fine tuned on a specific task by adding task specific layers and training the model on a smaller task specific data set. For instance, if the goal is to perform image classification, the model can be fine tuned by adding a classifier head and training it on the labeled image data set. And the result of this process is a powerful model that has learned to understand the relationship between images and text. And this understanding can be leveraged for a wide range of applications such as image and text classification, image-based search, and zero-shot image to text and text to image generation. So how do you calculate this clip by hand? So there's contrast language image pre-training model, which is a groundbreaking work by OpenAI. It redefines the intersection of computer vision and natural language processing. It is the basis of all multimodal foundations we see today. So how will we work? First, we will have to learn a shared embedding space for text and images. So consider we are given a batch of 3 text image pairs, right? This is the text, this is the image, text, image, text, image, right? So OpenAI uses 400 million text image pairs to train its original clip model. So we will process first pair, that is a big table. The second step is to convert this text to the two vectors. So look up the word embeddings using word2vec. So big, we will write the big here like this table. So mini, chair, top, head like this. So the word embeddings shall be, first comes the big here, then come table, then mini chair, then top head like this, right? Then you will convert this image to the 2D vectors. That is, you will divide the images in two patches and flatten each patch. So also here, so you have taken this and have flattened the things. So here we have taken this images, divided it into two. So 2, 2. Here also it's taken 2, 2, and we have written the things like this. In the next step, we have text encoder and image encoder now. So we will encode input vectors into feature vectors. Here both encoders are simple one layer perceptron, that is linear plus ReLU. So in practice, encoders are usually transformer models. So consider like this, we have the weights and the biases, and this is the input matrix. So do the product multiplications. So 1 into 1 1, 0 into 0 0, and 1 into 1 2. So answer should be 2 because it shall be bias, it shall be at wx plus b. We know that the formula for this y here also will calculate like this. So multiply here, it's 0, it is 0 and 0, and plus minus 2. So minus 2 shall come here. Here also multiply the 1 1 0 with 1 0 1, get the output, adding bias here, right? Now as we are using the ReLU here, so consider all the negative terms as 0, right? So minus 2 should be considered as 0 here. Here also for the image encoder, we will do element wise multiplication. So here 1 1 0 0 will be multiplied with 1 here, adding 0 bias, that is y is equals to wx plus b. Okay, so remember this formula, y is equals to wx plus b. Okay. So here also we will do the same thing, that is w is the weight of the matrix, x is the input, b is the bias here, right? So here when we are multiplying this, we are getting like this, okay, right? Next is mean pulling. Mean pulling means we are just averaging the things. So 2 plus 1, 3 by 2. It should be 1.5, but approximately, and the round off, it should be 1 here. So here also 0 plus 1 by 2.5. It should be approximate to the 1 here. Here also multiply like this, 0 plus 1 by 2, 1 plus 1 by 2, like this we have done. Here also we have done the same thing, 2 plus 2 by 2, 2 plus 3 by 2, right? Like this. Next step is the projection. Now note that the text and the image vectors from the encoders have different dimensions, 3D and the 4D. So use a linear layer to project this image and text to the 2D shared embedding space, right? So here consider this as a bias here, y is equals to wx plus b. So multiply this 1 1 0 with the 2 1 2, adding the minus 2 here. We'll get the results like this. Here also minus 1 1 1 this, multiply this with this one and adding the minus 1 as the bias here. Done this. Next we will prepare for the matmul, that is copy the text vectors and copy the transpose of this image vectors. They all are in 2D shared embeddings. So you will multiply this transpose and this image matrices. That is, you are taking the dot product between each pair of text and the image purpose. The purpose is to use dot product to estimate the similarity between the pair of text and the images. So here we will just multiply this 1 1 multiplied with the 2 0 like this. Done a simple multiplications here, right? Now we will take a softmax. Softmax means we will take 3 ki power this, 3 ki power 2 9, 3's power 0 is 1, 3's power it should be minus 2, that should be 0, like this. Now in the next step we have simply added them like row wise and the column wise. So here 9 plus 1 10, 3 plus 1 4, like this. So here also we have done multiplication additions here. So row wise addition, 9 plus 3 plus 27 39, like this we have done, right? So next we'll get the things like this, right? And here we will get the softmax, that is we will divide each element by the column sum to obtain the similarity matrix. So how will you calculate the similarity matrix? That is divide this 9 by this 39 like this, just divided by the totals. So here also to calculate the similarities, divide each individual elements by their sum here, right? We will get both the things. Now we'll have a target matrix, right? The targets for the similarity matrix are the identity matrix. Why? If I and T comes from the same pair, we want the highest value, which is 1. So apply the simple equation of similarity minus target to compute this gradients for both directions. Why so simple? Because when softmax and the cross entropy losses are used together, the work magically works here, right? So when you will get this thing, right? So you will use this key, that simply minus, like minus 2 sorry, 0.2 minus 1, that is minus 0.8. This minus this minus, you will have to subtract this target from this matrix and we'll get this red matrix here. Here also you'll do the same thing and then we'll get the results here, that is 0.9 minus 1, that is minus 0.1 here. So this way you will calculate the things. So if we summarize this, we have got this mini batch of text and image pairs. We have taken it like this, mini, big, like this. So we have taken first big table and then mini chair top head like this. The here done with the element wise multiplications using this formula wx plus b. Here also taking the same thing, then doing the mean pulling, that is 2 plus 1 by 2, like this we are doing the things. Then projection, that is using the same formula wx plus b. Here also using the same formula. Next we are taking this image and the transpose pairs here, do the element wise multiplications, get the things like this. Then we will take a softmax matrix. Softmax means 3 ki power 2, 3 ki power, like this. So we have taken this, done this element wise multiplications. So element like this, 9 plus 3 plus 27. So just addition row wise and the column wise, got the things. Now we will subtract these things by 9 divided by 10. So we have got the things. So in the first product we have divided each individual elements by this. Here we have divided these elements by this, like 9 divided by 39. So we are getting the matrices like this. Now we have target. So finally we will get the cross entropy gradient loss gradients by minus this one. So 0.9 minus 1, that is minus 0.1. So this way we have got the results here. So next comes the applications. So this contrastive language image pre-training model has a wide range of applications due to its ability to understand the relations between the text and images. So here are some of the key applications which I explained in simple term. The first is the image and text classification. So this clip can be used for classifying images and text. For example, you can use the model to classify images into categories like animals, vehicles or buildings, and to classify text into topics like sports, politics or entertainment. Second is image based search. So with clip you can perform image search using text queries. For instance, you can search for images related to a specific topic such as pictures of penguins and the model will return the relevant images. Next is the zero shot image to text generation. So this clip can generate text descriptions for images without being explicitly trained on a task. For instance, you have given the image of cat. The model can generate a text description like a cute white and grey feline sitting on a windowsill. Next is zero shot text to image generation. So this model can generate images based on text description. So given a text prompt like a picture of a delicious slice of pizza, so the model can generate a image of pizza. Next comes the image and text retrieval. So the clip can be used to find similar images or text based on their content. For example, you can use the model to find images or text similar to the given input, such as finding other images of penguins or similar articles on a given topic. Next comes the multimodal learning. So the clip model can be used for multimodal learning, where multiple modalities, example text, images and audios, are used together to solve the task. For example, you can train a model that can perform speech to text translation by combining clip's text image understanding with a speech recognition model. The next comes the general purpose pre-training. So the clip can be used as a pre-trained foundation model for various downstream tasks in the computer vision and natural language processing, such as object detection, image segmentation, and question answering. So these are just a few examples of many applications of the clip model. Its ability to understand the relations between the text and images makes it a versatile tool for various fields including computer vision, natural language processing, and multimodal AI. Thank you.